So today we're going to be looking into liquids and solids. Now this is a continuation on a lot of ideas from our previous chapter dealing with gases. But while on gases we looked at how those gases behaved with respect to the temperature changes, here we're going to add into our discussion why things are solid, liquid, and gas. Like for instance, H2O. We know that's definitely a liquid at room temperature. That's one we all know. But if I just go down the periodic table to H2S, I want to be in a position where we can actually predict if we'd expect it to be a solid or gas. Turns out that one's a gas. All right, so let's get some terminology down here that we're going to use. So for the most part, our factors that affect our physical state are the identity of the chemical, the temperature, and the pressure. And we're going to remove 2 and 3 from most categories because we're going to do these at room temperature. So the temperature is around 25 degrees Celsius and the pressure is right at 1 atmosphere. And so when we normally talk about phases, we're talking about at those conditions, room temperature and 1 atmosphere. So that's why, we got plenty of solids, liquid, and gases at room temperature. All right, the next thing we're going to remind ourselves of is our phase changes and the terminology with them. Now the first 4 are common sense ones: melting, freezing, vaporization, condensation. We've all seen those for a while, but the last 2 are ones that might be refreshers. So sublimation and deposition. That's what's happening on our car windows in the winter. So when you get up in the morning, there's ice all over the windows. That's happened because the moisture in the air went through deposition and actually formed a solid on the glass. And if you don't bother to remove it, when the sun comes out, if it still stays cold, that sun will cause that ice to go right to the gas phase. It won't actually melt; it'll just sublime and become a gas. All right. Next thing to look at is what does it mean to be solid and liquid, and technically it all deals with how close the molecules actually are. So in a solid and liquid, the densities are really, really high by comparison to gases, and what that is telling us is that the atoms themselves are very, very close together. Something else that can confirm that is that we really can't compress solids and liquids too well, not compared to gases. Gases we can compress quite easily. Heck, you have that in your car tires, and if you need to, you can go to any gas station and add air to your tires. There's nothing even all that complex about that process anymore. But compressing a solid or a liquid is almost impossible. But if you look at the actual densities of solid and liquid, they all stay approximately the same for a given sample. So like CO2 gas, CO2 liquid, 44 grams of it does occupy roughly 30 milliliters, regardless if it's a solid or a liquid. Yet the gas can be as much as 25 liters, so about 1,000 times more. Matter of fact, when we actually list densities of solids and liquids, we typically see them listed as grams per cubic centimeter or grams per milliliter. And that's really because a cubic centimeter and a milliliter are pretty much the same size. So when water is listed with either one, that unit's almost interchangeable. Yet gases, they tend to list those densities in grams per liter, because increasing that volume by 1,000 moves that decimal 3 places, so we get with much bigger numbers. Okay, and the other weird thing that we see going on here with solids and liquids is when we go through a phase change, it turns out to get a liquid to a gas always requires more energy than going from a solid to a liquid. We have water down here. What I'm talking about is the energy needing to put into an ice cube to turn it into water. So ice cubes exist at 0 degrees Celsius. Water could exist at 0 degrees Celsius. Well, it takes some energy to change that ice cube into water, and that's roughly 6 kilojoules per mole. But to go from water to steam, both at 100 degrees, requires almost 7 times the energy. And regardless of the substance, pretty much every substance, it's much, much more to go from liquid to gas than it is to go from solid to liquid. Okay, everything that we see, though, can be explained by understanding intermolecular forces. Now, intermolecular forces are different than intramolecular forces. Intramolecular forces are our bonds. So a molecule like water, for instance, H2O, the actual lines between the hydrogens and oxygens are intramolecular forces or covalent bonds. Intermolecular forces is what's going on if I put another water molecule in there, and we're going to talk about how these two are attracted to one another. Because it turns out they actually kind of are. And the stronger the intermolecular attractions are, the higher the boiling points and freezing points are. Alright, so we're going to spend the next few slides talking about intermolecular forces. Alright, our basic ones that actually are easy to understand are dipole-dipole interactions. Now these are going to happen anytime you have a polar molecule. Now we have very simple ideas here. If you notice, this looks like it's just two atoms, and it is. But it's a polar two atoms. And how do we get something that's polar? Well, we have to have two items that have a large difference in their electronegativity. So maybe this is something like HF. Because if you remember, our electronegativity, fluorine is a lot more electronegative than hydrogen. So all the electrons spend their time hanging out in the fluorine. That actually makes that side of the molecule slightly more negative. Now, still a negative cloud. So what they end up saying is it's partially more negative, partially less negative. That's what those little bi symbols mean. It's a negative and a positive, but there, that looks better. All right, now when this molecule gets like that, it will arrange itself near similar molecules in such a way that the attractions line up and the repulsions get away from each other. Kind of like what would happen if we had a bunch of magnets laying around. They would arrange themselves so that their north and south ends are near, and their north to north, or similar sides, get away from each other. Well, those, in this case, these blue lines, purple lines, the attraction lines, are the intermolecular forces. You need to overcome those if I want to actually boil this particular substance, this liquid. Now, this is going to happen anytime you have a polar molecule. So as long as you can identify that a molecule is polar, it's going to have dipole-dipole interactions. Alright, that's going to help us understand what's going on with something like ICl versus bromine-bromine. Because I chose these two because ICl is made up of our halogens, and just two of them. And bromine-bromine is also halogens, and it turns out iodine and chlorine are just on the opposite sides of bromine. They split it. And these two molecules have almost the exact same molecular weight. So they weigh about the same. They are almost the same in size. But we see something drastically different. At 0 degrees Celsius, this thing, the iodine, is a solid. And yet the bromine is a liquid. The only reason that difference has happened is because the ICl is more electronegative and it's got a more polar bond. It's actually, the chlorine's more electronegative, so it's got that little arrow pulling all the electrons to the chlorine. That creates other dipole interactions with itself, and so ICl is attracted to other ICLs much more than bromine is, because bromine is a nonpolar molecule. Alright, the next type of dipole-dipole interaction is a special subset. So it turns out hydrogen, being our atom or nonmetal with the lowest electronegativity, or one of the lowest electronegativities, if we bond it to any one of the three highest electronegative atoms, these are the three highest, if we bond it to any one of those, we get a very strong dipole-dipole interaction. It's actually stronger than it would be predicted normally, so we gave it its own name. We call it hydrogen bonding. Now, it doesn't mean the hydrogen's bound to it. It's the hydrogen bonding is the intermolecular force between other molecules. So when I had water up there before, we actually talked about we were going to focus on the attraction. The attraction between two water molecules is what we would call a hydrogen bond. And it's very strong, much stronger than dipole-dipole interactions. Alright, now, How strong is it? Well, it's strong enough that we actually see very high boiling points and melting points for anything that has a hydrogen bond capable in it. And we see high solubility with things that have water. Now, it's not always, there are times that override, but typically if you see an OH, NH, or an HF in a molecule, it's going to have very high solubility of water. All right. Compared to other attractions, these are some of the strongest ones. They're about 5 to 10% the strength of a typical covalent bond. So the water molecules themselves, the actual bonds between the O and H, are stronger than these attractions. But the attractions are very close to being 5 to 10% of that overall strength. Matter of fact, it's so important that when we look into biology point of view, so everybody knows what DNA is, it has that nice little double strand. Turns out the strands are not actually physically connected to each other with bonds. They're attracted to each other with totally just hydrogen bonds. So just attractions. And even proteins, so even something as big as hemoglobin, which is several tens of thousands in the molecular weight, has a lot of different little subsections in it. There are a few proteins that connect to themselves. There's only one, cytosine. It connects to other cytosines in the structure. But all the rest of that structure, hemoglobin-wise, is held together with intermolecular forces. Okay, some other things that we can see. Turns out water has very unique properties compared to other things with similar molecular weights and similar arrangements of atoms. So that's what the nitrogen, oxygen, and the CO2 are. They're trying to get ones that are similar in how they are structured. But it turns out water is nowhere like those in the actual behavior. It has a very high boiling point, and yet all three of those gases are definitely gases at room temperature. They haven't been liquids for a long time at room temperature. Water has a very high heat vaporization and very high specific heat. Holds a lot of energy when we're trying to heat it up. And it is what we consider a universal solvent. All right. But I think this shows a little bit more of what we're seeing on these hydrogen bonds. So what we have on this chart is the boiling points of anything in the family underneath oxygen in the periodic table. So H2O, H2S, H2SE, H2TE. Anything under fluorine, HF, HCl, HBr, HI. And anything under nitrogen. So NH3, PH3, ASH3, SBH3, and then we went ahead and did the whole thing with carbon and everything under it. Well, if you remove these guys, the three that have hydrogen bonds, you see how predictable all the behavior is for dipole-dipole interactions. Most of those guys are just having dipole-dipole. Well, the bottom one is nonpolar molecules, but the three are just dipole-dipole interactions. Very predictable behavior. But if we were to stick with predictability, we would have actually put the boiling point of water at, what's that, about negative 80? And obviously it's closer to 100. All right, so that's our second type of intermolecular forces. Hydrogen bonds are very important to understand why they get higher boiling points and such. All right, and our final one is dispersion forces. Turns out nonpolar molecules do have attractions to one another. What happens in a nonpolar molecule? We have that electron cloud, and what happens is the electrons get unevenly distributed. So what I mean by that is maybe this guy happens to be over here a little bit more often. And if that's the case, this side of the molecule is slightly more negative for that moment than this side. Now, that does create a dipole, or a polar part of the molecule. But it's temporary. And in just a second, it'll go away, and we have a different positive and negative somewhere else in the molecule. But those momentary dipoles create small attractions. What's going to factor into making it a stronger attraction is just flat out more molecule. So a heavier or larger molecule is going to have more chances of having those electrons unevenly distributed, and then therefore a stronger dipole. So we see London dispersion changes with molar mass, first of all. The bigger the stronger the attractions are. Now, that does enter into a interesting little side step here. So CaH18 is octane. And octane, I'm going to draw one form of it. That basic form would just have 8 carbons in a row, and all the hydrogens are distributed as well as they can be. So this guy that I'm drawing, let's see, 1, 2, 3, 4, that is standard octane. Now, nice straight chain, has a relatively high boiling point, and it does to some degree end up in your gas tank, but that mostly ends up in diesel because it has a high enough boiling point, ends up separated out with diesel instead. And it's not to be confused with what you see on octane ratings, because it turns out the octane rating system, what they're trying to get in high numbers, it's still an octane molecule because it has 8 carbons, but they're arranged differently. All right, what's so weird about this? These two molecules have the exact same molecular weight, but the top one we call isooctane, at least that's what they say in the fuel industry. Isooctane has a much better performance in a car. If you were to run that in your car is going to run nice and quiet and smooth always. They call that, that's what the octane rating's about, is how quiet and smooth the car runs. Turns out, if you filled this up, your car up with this, apparently has an octane rating of like -10. So I think that actually means your car just basically sounds like it's falling apart as soon as you start it. It does end up in your gas tank, but there's 30 components in our gas, so small amount of that is not that big of a deal. Alright, so our forces between molecules explain a lot. They explain why we have different properties for different gases, but they're all related to those molecular structures, because the molecular structures can tell us what the attractions are like. And we can, because if we understand this, we can see the control over it. So we can actually liquefy most gases. We just get them under a lot of compression. We force the molecules close enough that suddenly the attractions become important. And that's what we do in like CO2 fire extinguishers. Technically inside there is liquid CO2 at room temperature. It's just under such high pressure that it's forced the CO2 to come together, and it behaves more like a liquid. If you were to just pull the lid off, that CO2 would actually evaporate quite fast. Alright, let's relate this too. So along with molecular weight affecting our boiling points and freezing points of London dispersion forces, it also does that with dipole-dipole. But typically, when you have a polar molecule, the one that's more strongly polar is going to have a higher boiling point. Now, weight does factor into that. A larger molecule that's also polar, even if the polarity is not as strong, might overlap. And we'll do some more of those overlaps in a bit. But right now, I want to focus on something where the molecular weights are the same, but you might have different dipole moments. Alright, so what I have down here at the bottom, I got the structures of 3 molecules that have the formula of C2H2Cl2. The carbons aren't labeled, but they're the intersections. That's how they do this in organic chemistry. You never label the carbons because everything in organic chemistry has a carbon. Alright, but if you notice, this double bond is something that doesn't rotate, or doesn't rotate without breaking. So having the Cl's on the same side as this is a totally different molecule than having them on opposite. Now this one's obviously different because that has both the chlorines on this one carbon. Both these had them on 2 separate ones. Alright, so when they're on the same side like this, the organic chemists call that cis. And when they're catty corner like this, it's trans. Alright, we see something interesting about the boiling points. These two actually do have different boiling points, even though they have the exact same chemical formula and the exact same molecular weight. The reason they have different boiling points is because the dipole moment here and here technically end up canceling out. This thing is mostly nonpolar. This guy, though, they can't cancel out because the vectors kind of add up together. This is still a polar molecule. So this actually has dipole-dipole interactions. And just because of that, it has a higher boiling point. All right, next one. We're going to actually just say that when we actually assign our intermolecular forces, these are the classes we find. These are the three classes we find: traction between molecules. Now there is going to be overlap, because you can have things that have hydrogen bonds, like water, mixing in things that are just polar. And even to a degree, we can sometimes mix water with things like gasoline, but we typically know those don't really mix. So we don't get a lot of mixing between classes, but there is some. Now, we can see that on certain properties, but we're going to look at that in just a second. But first, we're going to talk about some of our properties we've been talking about and relate them to what we've been talking to. So first thing we're looking at is the boiling point. More specifically, we're going to look at what we call the normal boiling point. Because it turns out you can boil things at a lower temperature or higher temperature based on modifications you do in the lab. Like, for instance, if you were to boil water here in the lab, it's going to boil around 100 degrees Celsius. But if we were to take that same beaker and try this in Denver, the boiling point is going to be much, much lower. Well, not much, much lower. It's going to be lower, but that's simply because the atmospheric pressure is low. Normal boiling point is when the atmospheric pressure is right at 1 atmosphere. But if we change the atmospheric pressure, boiling point does change. Matter of fact, we do this neat little thing in the lab. So we have these weird little flasks look like kind of triangles, and they have these little necks on the side. They're called vacuum flasks. But if I put water in here and then seal this up and then hook this up to the vacuum, I can actually get the water boil even at room temperature, because I can drop the vapor pressure down, or I can drop the pressure down low enough that water's boiling point is at room temperature. It is neat to do that, because then, let the students touch the flask and everybody's afraid it's going to feel like it's hot, but it's still room temperature water. It just is boiling. So it is a pretty neat little effect. Okay, so here's where I'm talking about with the overlaps, though. So what I mean by overlaps, it turns out some things that are London dispersion forces only actually do have higher boiling points than things like water and such. A good example of that, the roads outside, asphalt. Turns out asphalt is mostly made up of hydrocarbons. Matter of fact, one of the additives that they're putting into our roads now is basically, once they've actually recycled our car oil, the parts of the stuff that's unusable, the really thick sludge that comes out the bottom, ends up as part of asphalt, because that's all asphalt is. It is really a hydrocarbon. It's just really, really, really high molecular weights. Now, the neat thing about asphalt, though, is because it is like that, it does create some odd little problems. Like, I don't know if you've ever noticed, but you go to like Target or Walmart, you'll sometimes see the people with their motorcycles park their motorcycles on the sidewalk up by the building. We've seen a few times where some person who doesn't need to say anything goes up and yells at that person with their motorcycle for not parking in a spot. But biggest reason they do that is their kickstands will sink into the asphalt because the weight of their motorcycles are just so much, and the asphalt is soft on small approaches like that. So they'll go out and their motorcycle will be on the ground simply because it sank into the asphalt. But we're just showing that to show that overlap. There is overlap between those. Now, also on here, at the very top, we have some forces we didn't talk about, ion-ion, Well, we did actually. That is an ionic bond. Now, ionic bonds are an intramolecular force, but they're also inter, because they are just attraction between the different ions. So, ionic bonds are kind of inter and intramolecular forces. All right, but the one that we've added on this, which is kind of neat, is that ion dipole. That's like when water gets added to salt, or salt gets added to water. That water does actually interact with those salt crystals, and it creates an ion dipole interaction. Now, ion dipole is not really from any particular atom or molecule. It's all by itself, at least not yet. So it is typically mixtures. All right, so next little thing. Last chapter we introduced the kinetic molecular theory to help us understand why gases behave the way they do. Now, we actually said back then that the attraction forces between gas molecules could be ignored because the speed of the particles and the distance between them was so large that it was a negligible attraction. Well, that is still true. What's kind of neat, though, is when we slow that molecule down, or that particle down, we will get to the point where eventually the attraction forces are important. And the reason we can still say gases are removed from this is because as soon as the attractions get important, you condense your gas to a liquid. So when it's a gas, the particles are moving so fast that you can ignore those intermolecular forces, but as soon as the intermolecular forces come into play, you've cooled enough, and you are pretty much going to be a liquid or a solid if you cool it enough. All right, let's see if we can understand what's going on some of these things. So let's see if we can understand the difference between the boiling point of acetone and propanol. Now, if you were to get something like this on the test, you would also get a Lewis structure of those molecules. So acetone has 2 carbons with 3 hydrogens off each, and in the middle there is a carbon double bonded to an oxygen. That is acetone, also known as fingernail polish remover. Propanol, there's a few propanols. You're probably familiar more with 2-propanol, which is isopropyl alcohol. But 1-propanol, it's also 3 carbons. And on the very first carbon, which I left a spot there, there is an O bonded to an H. It's an alcohol. All right. Now, can we use anything we've actually learned so far to explain why these two things that have very similar molecular weights have totally different boiling points? Well, yeah. Now, I do see this thing. Because of the double bonded oxygen, that molecule is going to be polar, and therefore it does dipole-dipole interactions with itself. But this has an OH in it. So this does hydrogen bonds. And just because of the hydrogen bonds, you get those much higher boiling points. All right, how about a couple? I got N-butane. So butane lighters. N-butane does just say that there is a straight line of 4 carbons, and each carbon has the remaining 4 sides of it surrounded with hydrogens. N-butane. Chloroethane. Ethane is just 2 carbons. And being that it's chloroethane, means off the first one is just a single chlorine. Weight of these 2 molecules is about the exact same, but why would chloroethane be a higher boiling point? Well, this one's totally nonpolar. So this is just those London dispersion forces. Yet, that electronegative difference right there is going to make this thing polar, so this has dipole-dipole interactions. Alright, how about this? this is a type of question that I could give you in the test and expect you to be able to figure it out without giving you the lowest structures. All right, so if we want to rank highest boiling points to lowest boiling points, we're actually going to have our highest be the ion-ion. And I would have ion-dipole, but that's not really a possibility if we're looking at individual components. So after ion-ion, there is just hydrogen bonds. And then there would be dipole-dipole. And then London. Alright, so ion-ion is any ionic compound. That's this guy. And that's our only one, so that doesn't help us. All these have ion-ion. Do you have anything there that would be hydrogen bonding? Yeah, HF fits in that category. So it's probably the number 2 on the strongest, on the highest strength. And do we have any dipole-dipole? Yeah, the carbon monoxide. That doesn't help us because that puts both those together. So the last two is hydrogen and neon. Now what type of force would they put in? Are they both London? Yeah, they pretty much are. So hydrogen-hydrogen is a nonpolar bond. Neon is just a noble gas. The only thing those are going to do to create their attraction is those London dispersion forces. All right, but how do we tell them apart? It really is just the molecular weight. Hydrogen being the smallest is going to be the smallest, or the lowest boiling point. All right, last little topic here, vapor pressure. We're going to apply it to it. Now, when we talk about vapor pressure, what we're talking about is controlling evaporation to a degree, or that's a good way to think about it. So if we were to actually have an open container that has water in it, eventually that water would totally evaporate. But what we're going to do is put a cap on it. And if we do that, eventually the water would actually get to an equilibrium and would stop evaporating. That vapor pressure is the pressure that's built up inside there. If we had a gauge on here, we'd see a certain pressure, and that vapor pressure does increase with temperature. Now, all liquids do this. All liquids do evaporate. Some just have a higher vapor pressure than others. It turns out the higher vapor pressure is related to those intermolecular forces. Water turns out to have a relatively low vapor pressure to many liquids we know, simply because it has stronger intermolecular forces. Other liquids I was thinking about things like gasoline. Gasoline has a relatively high vapor pressure because it has weaker intermolecular forces. Alright, so we can make a call based on those intermolecular forces, and this is talking about water here on this page. But what we also want to talk about is how it varies with pressure. So what we're looking at is we're going to take that container, we're going to put a lid on it, and we're going to see that the evaporation and condensation gets to an equilibrium eventually, and it's going to be a very particular pressure. Now you can see this even on a bottle of water. If you were to take a bottle of water out of your refrigerator, for instance, and open it up and then reseal it, so get the pressure equalized inside there, and just leave it out. As that water warms up, you'll notice the pressure gets more. Now it's not going to be dangerously more, it's more, and when you open it you actually hear that gas escaping. That is actually water vapor that's built up. And it is theoretically possible to heat your water up inside to the point where the top would break. And yeah, you wouldn't necessarily want to do that because that could actually release a bunch of very, very hot water. But yeah, it would happen. It does actually eventually fail. Alright, so last little thing. We're going to see if we can actually apply this to our intermolecular force concept. So I have cis-dibromoethane and trans-dibromoethane. So I'm going to draw these out. The dibromoethane is very similar to the dichloroethane we had before. Cis would have them on the same side. Trans would actually have them opposite. Alright, so to answer this question, we need to know which, if one of these is going to have dipole-dipole interaction, or is it going to be London dispersion. This guy that has them opposite is going to be a nonpolar molecule. This one over here is dipole-dipole. just because of the difference in the intermolecular forces, we can say this one is a stronger intermolecular forces. And because it's stronger, it actually has lower vapor pressure. So the one with higher vapor pressure is the trans. Okay, that gets us done with our liquids and solids chapter. Got quite a few sample problems to look at. Send me an email if you have any questions.